Topic Notes 1.1, Particle Theory and Bonding. This picture is of one of my favorite beaches, MacArthur Beach State Park, and really any beach you go to, you are surrounded by water. Both in the ocean, you have liquid water, and in the atmosphere, you have water in its gas form, as in water vapor and in droplets making up the clouds, and even some ice crystals up there in the higher atmosphere. It's really important as we're studying the ocean to understand the medium in which we are learning about. So that is why we are starting with chemistry. As always, if you're starting to learn something new, it's good to have a roadmap. And here that is. You have a section of main ideas at the top and then specific learning goals through the bottom. Now let's go over the main ideas before we get started. We want to understand how matter is a collection of particles that are in constant random motion. Also, that the amount of motion affects which state, solid, liquid, or gas, matter is in. Atoms form bonds due to the interaction of electrons, sharing, exchanging, or electrostatic attraction. The polar nature of water molecules causes unique properties that are important to life on this planet. Now that we know what we're up for, let's get started. You may have heard this quote before, but 71% of the Earth's surface is covered in water. That really does make us the water planet. 97% of the water on the planet is ocean, which really makes it one big ocean world. In fact, that means the most habitable space on our planet is the ocean. And it's not just water and table salt, right? Seawater is made up of a complex mix of chemicals. So that's why we're going to be starting with chemistry. So now it's time to get down to business and start learning about chemistry and specifically matter. Now, the first thing I want to talk about is the kinetic particle theory, which describes all matter as a collection of particles that are in constant random motion. Now, you probably all remember the smallest unit of matter is an atom, right? So the definition is an atom is the smallest particle an element can be divided into while remaining the same substance. Now we can get back to that idea of the kinetic particle theory with the matter moving around. You've heard of states of matter before, probably back in middle school. Matter exists in 3 states: solid, liquid, and gas. The state of matter changes as energy is transferred into or away from molecules. Essentially, we're talking about molecular motion. So let's start with an example. Let's say you have ice, which is solid, right? And you start adding thermal energy to that. So the little molecules within the ice block start to vibrate, and eventually they increase that molecular motion until we change state to a liquid. Now we don't stop there, we crank up the burner, if you will, and add more energy. And as that happens, the molecules start to vibrate faster and faster until some of them start to escape the surface of the liquid and they transition to a gas. We also know this as water vapor. Now let's look at the atom a little closer. Atoms are made up of 3 smaller subatomic particles. You know them, you love them: protons, neutrons, and electrons. Protons being the positively charged particles being found in the nucleus, and neutrons being the neutral particles, again, contained within the nucleus. Electrons are the negatively charged particles that orbit rapidly around the outside of the nucleus. Now, of course, the ratio of protons, neutrons, and electrons results in the very specific characteristics and properties that each element has. Now, atoms are very small, and when scientists are dealing with things that we can't really see or observe very well with our own senses, we use models sometimes to really understand the very, very small, like atoms, or sometimes the really, really large, like whole galaxies and such. And the atom that we're going to be learning about, we're going to be looking at it through the lens of models. And models help us understand and predict the behavior of these atoms in different circumstances. So we know the atom has essentially a nucleus, which is a positively charged center core of the atom that is made up of protons and neutrons. Now around that are the electrons, and we call these electron shells. And they are essentially each of a set of orbitals around the nucleus of an atom that can be occupied by electrons. Now let's look at one of the most ingenious tables ever designed by science, and that is the periodic table, which lists all the known types of atoms called elements. Now an element is a substance that can't be chemically broken into a simpler substance. Now the atomic number is the number of protons contained in the nucleus of an atom. And like I said, the periodic table is ingeniously organized, and it is done so through the atomic number. So the elements are all arranged that way. Hydrogen on the top left has an atomic number of 1. If you follow the gap across in the same row, you will find helium on the right with an atomic number of 2. In the second row, called a period, there's lithium with an atomic number of 3, and then so on and so forth. Each period or row essentially represents an electron shell. For example, hydrogen and helium have 1 electron shell. Lithium, beryllium, and so on have 2 electron shells. So why do we need to know this stuff? It all comes down to bonding, and that's what we're going to talk about now. A bond is a strong force of attraction holding atoms together in a substance, such as a compound. Now, a compound is a substance formed when 2 or more elements in a specific ratio are chemically bonded together. An example of this would be water, H2O, and water essentially has 2 hydrogen atoms and 1 oxygen atom. So why is bonding important? Well, as it turns out, if you put 2 or more elements together in a bond, they actually come up with characteristics that neither had before. This is called emergent properties. And we see this with water itself. Now, because water is so important, we're going to spend a lot of time with it. And the first bond we need to know to understand water is the covalent bond, which is a chemical bond that involves the sharing of electron pairs between atoms. This occurs in most what we call non-metal elements or compounds formed between non-metal elements. Both atoms have a complete outer valence electron shell. What does that actually mean? Now remember I said that atoms had a certain amount of shells around them that electrons are in. And of course, I talked to you about how hydrogen and helium had 1 shell, lithium and so on had 2 shells, sodium has 3 shells, and so on. Now, if you look at an element like neon with an atomic number of 10, it has 10 protons. Now, in a neutral atom of neon, you would actually have those 10 protons, and you would have an additional 10 electrons. The reason for that is the electrons, which are negative, counterbalance the 10 positive protons, making it a neutral atom. Now, if you notice, neon is at the far right of the table, and that column, helium, neon, argon, and so forth, are part of what we call the noble gases. Now, that's really important because these elements are kind of inert. They don't react well to anything. And that is because they have a full valence electron shell. Now, a valence shell is the outermost shell of electrons in an atom. So the number of electrons per shell is dependent on how many elements are in each row. For example, the first row or the first period has helium and hydrogen, 2 elements essentially in that row, which means the first shell of any element has 2 possible electron positions. Now the second period or the second row has 1, 2, 3, 4, 5, 6, 7, 8 elements in it, from lithium all the way to neon. That means that shell can hold 8 electrons. So neon has 2 shells. One, the first shell with 2 electrons, and then the second shell with 8 electrons. 8 plus 2 is 10, giving it the full 10 electrons. Now, unlike neon, sodium has 3 shells. It has 2 electrons in its first shell. It has 8 electrons in its second shell, but its third shell only has 1 electron, even though it could hold 8. That means sodium does not have a full valence electron shell, and sodium wants to react with something and bond with something to get more electrons, or lose an electron in this particular case, because that is where bonding comes into play, gaining and losing electrons or sharing electrons. Now, when we're talking about covalent bonds, we are talking about sharing electrons. Now, covalent bonds in general are very strong bonds requiring a large amount of energy to break. Now, covalent compounds can exist as solids, liquids, or gases. Here's some examples of covalent compounds that you should know about. Obviously, the first and most famous would be water, H2O, followed probably closely by carbon dioxide, CO2, sulfur dioxide, SO2, oxygen, which oddly enough is bonded with itself in the air as O2, and glucose, which of course is really important for energy and life and stuff, C6H12O6. So now let's focus on the water molecule itself, because that is a great example of covalent bonds. So in a water molecule, you have 2 hydrogen atoms covalently bonded to oxygen. Now, this is a special type of covalent bond called a polar covalent bond. Now, that means that the sharing is unequal, causing partial charges or polarity within the water molecule itself. So this leads to hydrogen bonds, our second type of bond we're going to talk about. Now, a hydrogen bond is a weak bond between 2 molecules due to electrostatic attractions between a hydrogen atom in one molecule and an atom of oxygen, nitrogen, or fluorine in the other molecule. Now, hydrogen bonds are one of the weakest bonds around. They easily break and form all the time. Now, in this diagram, you can see the hydrogen bond is between the 2 water molecules. It exists between the positive end of one molecule, which is the hydrogen end, and the negative end of the other molecule, which is the oxygen end. So why does this exactly happen? Well, oxygen is actually the key. Oxygen is what we call an electronegative element, meaning that it has a stronger attraction to bonding pairs of electrons than, say, the hydrogen does. And essentially what this comes down to is it doesn't share very well. It's kind of like if you ever had a friend when you were a kid and you were playing with toys and you would share and they wouldn't share very well. Well, oxygen is that kid that didn't share the toys very well. It doesn't share those electrons very well, meaning that it hogs those electrons around itself a lot, meaning that it has a couple of extra negative charges around itself, hence why it has a partial negative charge. So let's focus back in on the water molecule. This means the bonding electrons are unequally shared. They're pulled closer to the oxygen, which is electronegative, than the hydrogen. This causes a partial charge where hydrogen has a partial positive charge because it's kind of losing an electron most of the time and it just has the one positive proton, and the oxygen is gaining up to 2 different electrons most of the time, giving it a partial negative charge. These are not full charges, which is important to note. And we call these partial charges poles. Thus we have polarity. So the partial positive on one water molecule attracts to the partial negative on another, forming a hydrogen bond. Don't confuse hydrogen bonds with the covalent bond between an oxygen and a hydrogen within a water molecule. This is something students sometimes do. Now remember, we talked about emergent properties. So once you put the two hydrogen and oxygens together in a polar covalent bond, and you have hydrogen bonds on top of that between water molecules, you start to get very unique properties that are incredibly critical to life as we know it on this planet. One of those is that water is essentially liquid at room temperature. Without those hydrogen bonds, water would generally be a gas at room temperature, which would not work for our physiology considering we're mostly made up of water. There's also something called cohesion and adhesion. Essentially, this means that water molecules tend to stick together, cohesion, and they stick to other materials, adhesion. Now, these other materials tend to be polar materials as well. So you think of this, cohesion is those hydrogen bonds making the water molecules kind of stick together a bit, and adhesion is where they sort of stick to other surfaces. Then there's high surface tension, meaning that water has a resistance on its surface for objects attempting to penetrate it. The best example of this is very light insects that are able to skate across the water surface without breaking that tension. Water also has a high viscosity or resistance to flow. An example of this, if you've ever been in water before and you tried to run or move fast through it, it's a lot thicker, it's a lot harder, meaning it takes more energy for organisms to move through that water than, say, air. Now, this is a really important one. Water has a high specific heat capacity. Now, specific heat capacity is the heat required to raise the temperature of the unit of mass of a given substance by 1 degree Celsius. Water has one of the highest specific heat capacities due to that hydrogen bonding. This means you have to add a lot of energy to break up those bonds enough to increase molecular motion to go from a liquid to a gas, for example. Now, this provides a very stable aquatic environment for aquatic life and marine life specifically. Water acts as essentially a temperature buffer, moderating our entire planet's climate. Mild climates along the coastline are typical because of this feature. It's really an important one. Now, just as a comparison, on this graph, you'll notice heat added on the bottom in joules and the temperature increase on the y-axis. As you increase heat or energy added, you'll notice that the water doesn't change temperature as fast as the aluminum does. This is what we mean by water having a higher heat capacity compared to, let's say, aluminum. This next property of water you've experienced all your life. If you've ever held a glass of ice water, you've known that ice floats, right? And that icebergs float. Did you know that that's really weird? So before we explain why, let's talk about density. So density is the measure of the mass of a defined volume of water, or anything else for that matter, but we're talking water here. And its density equals mass over volume. That's the equation. Density equals mass over volume. Essentially, we're talking about how much stuff is in that particular amount of volume. For example, these images here, you see the low density has 2 molecules in it. Medium density, there are 4 molecules, and high density, you have a lot more molecules. So essentially, the higher the number of molecules per that same volume, the higher the density. That's how it works. Now, for most substances, when you go from a gas to a liquid to a solid, you increase density. That's because molecular motion is decreasing. From a gas to a liquid to a solid, the molecules move slower and slower, and they get closer and closer together. So you have more molecules per unit volume. Now, this is not what happens with water. Water is very strange because as water becomes a solid, essentially becoming ice, it becomes less dense as it freezes, which is very strange. So let's see how this works. As water nears the freezing point, which is 0 degrees Celsius, molecular motion slows. The molecules get closer and closer together, and then hydrogen bonds become stronger. Hydrogen bonds keep molecules at a perfect symmetrical distance from each other. Now, right before freezing, the molecules form a crystal lattice-like structure, and that essentially spaces the molecules farther apart, making ice less dense than liquid water. And because of that, ice floats on the surface. Ice cubes, icebergs, whatever. They are less dense than the liquid water that surrounds them. Yet, it's a solid, which is exactly why it's kind of strange. Either way, it's just another awesome property due to the polar covalent nature of the water molecule that causes hydrogen bonding. Now, this actually has some biological sort of ramifications because that ice, as it freezes on the top of the water, it actually creates a bit of an insulating layer that maintains and stabilizes the temperature under the ice. You see this a lot in northern lakes and ponds, but it also works in the ocean as well. Now, our next set of notes is going to talk all about salinity, but that brings up our next property of water. Water is the universal solvent. So what is a solvent? It's a substance which can dissolve other substances. This comes back to the polar nature of water. Remember, the covalent bond between the oxygen and the hydrogens within a water molecule is a special kind of covalent bond called a polar covalent bond, like we covered before. And that creates these partial positive and negative charges. These partial positive and negative regions within a water molecule help not only form hydrogen bonds, but it attracts other positive and negative ions. Now, this happens to be things like salts, sodium and chloride and magnesium and all those sorts of things. Now, oppositely, things that are nonpolar, for example, oil, they don't dissolve. And if you've ever poured oil in water, you'll notice how it sort of bubbles up and stays at the surface because it's, first of all, less dense and it's just not polar. So finally, we're going to get to our last bond, which is the ionic bond. Ionic bonds are chemical bonds that involve the attraction between two oppositely charged ions. In this case, one electron is donated to the other atom, and that causes the one atom to be positive, the other to be negative, and they attract each other. Okay, let's backtrack just a little bit here and define a few things. First of all, an ion. An ion is an atom or molecule that has lost or gained one or more electrons, creating an electrical charge. So this occurs because electrons move between atoms, resulting in either a filled or an empty valence shell. Remember, those valence shells are the outer electron shells in an atom. Now, a loss or a gain of an electron will create a positive ion, known as a cation, or a negative ion known as an anion. Now, this is because, remember, each element has a certain number of protons in its nucleus, right? That's the atomic number. Now, if you change the number of protons, you change the element from, for example, lithium to iron or whatever it is that you're doing. You change the number of protons, you change the element. However, if you change the number of electrons, it simply becomes an ion, but it's still that element. And that's the key thing. But now your positive and negative charge balance is now off balance. If you have extra electrons, negatives win out and the atom becomes negatively charged. If you take away electrons, then the positives win out and it becomes positive. Now, a great example of an ionic bond, and of course a great example for marine science, is the formation of salt. Now, you know it as sodium chloride, which is table salt. And both sodium and chloride have incomplete outer shells. Sodium has 1 electron in its outer shell, where chlorine has 7 electrons in its outer shell. Chlorine can actually have up to 8 electrons in its outer shell, so can sodium. So it's easier for sodium at this point to get rid of 1 electron than to gain 7. Whereas chloride, it's easier to gain 1 than get rid of 7. So essentially that makes sodium and chloride great partners for making this ionic bond. So let's go through this step by step. Sodium's single electron will break away and transfer completely to chloride's outer shell. Now, sodium is positively charged and chlorine is now negatively charged. both with full outer shells. So the electrostatic attraction creates that ionic bond between them, between the full positive and the full negative charge. Remember, this is not like hydrogen bonds where there's partial charges. This is a full charge that's attracting these two together. Now, interestingly enough, many atoms of sodium chloride can react together and create solids with a 3D ionic lattice structure that essentially is cubic. And this is kind of cool because when it dries, essentially when you have salt water and it dries up through evaporation and it forms crystals, those crystals are in cubes. And there are many types of salts found in the ocean, not just sodium chloride. There's calcium carbonate, there's magnesium sulfate, and so on and so forth. And we're going to learn a lot more about that in the next note set, all about salinity. All right, that is it for this note set. Remember, this is a good time to take a moment and review what you've learned. Use these main ideas that we covered at the top of the note set and identify all of the different learning goals that we addressed during this note set as well. And until next time, keep learning.